Anyone seen that GCHQ box outside the factory?
Yeah.
Oh, is that what that is?
I'm too scared.
I didn't know what it was.
It's a challenge.
I've dealt with it. It might have to.
I don't know anything about maths, so I don't know.
It's because they've got a deadline today for graduate positions.
Deadline today, so they're advertising it today.
I think Linda said it was
Bit
next week.
ambitious.
Yeah,
It's at the end of February.
Hey,
It's
we've
not
all been
quite
down
yet,
that
it's
one.
just.
I think they're on a tour around, yeah.
Oh, I didn't bring any papers.
They have set up
What's
a,
that?
they have set up a base in Manchester.
Yeah, you
apparently,
got to
so,
complete
Yeah.
the circle, but it's something to do with the
Yeah.
secret base.
yeah.
I don't know if that's the.
Everybody know where it is?
Yeah, to be honest.
It's something.
I just saw take the challenge and I was like,
It was such a bright box as well. It's like, it's too intimidating.
LEDs for holding level.
Okay,
Just going through course with today.
so, good to see you all again.
For mischief.
Yeah.
Can you reteach all these chapters?
Yeah, can we do the last six weeks again?
Well, we've got revisions.
I will recap a little bit on group actions, because that's where we're going to pick up group actions and run with it.
We're not going to try and run them for you.
You literally just ran. You literally just ran.
When?
Yeah, you just raced ran through the courtyard.
Oh, yeah, I did.
Okay,
I was like one of the things.
Already.
so, the first real substantial theoretical result we proved about groups was Lagrange's theorem, which says,
Oh,
The order of the subgroups must divide the order of the group.
I didn't know that was a
Is that
question.
an-
I
is
was
that
just quizzing.
Is that an adequate exam answer? Lagrange's theory?
I would have preferred
It's.
this phrase to begin, so it applies to finite groups, yeah?
Alright.
G is finite, and H is a subgroup of G.
Surely it's still true if it's not finite.
Well, then there's nothing to divide.
Yeah,
Yeah.
yeah. I mean, it's a non-statement, but it still holds.
It holds better than
Can
mine.
you just write
My
if G
answer.
finite rather than the size of G finite? Because it means the same thing.
Indeed, yeah, that would mean the same thing. Yeah. Yeah, you should, we can say the phrase a finite group means it's of finite size. Yeah.
Oh, yeah.
Okay, so e.g. if the size of the group happens to be 15, that many different groups of size 15, but the size of the group is 15 and H is a subgroup of G, then the size of H is one of, has to divide 15, yeah. So, you know, one of the main ways we think about Lagrange's theorem is it limits the possibilities for subgroups, yeah. You can't have a subgroup of size 4, size 8, size 10. Right? There's a limited range of possibilities for the size of a subgroup. Obviously, this size 1, it is there, yeah. There's the trivial subgroup, the subgroup just consisting of the identity element that contains one element. Size 15, yeah. Also, trivially, the whole group is a subgroup of itself. Okay. So the pressing question for a group of size 15 is: does it have a subgroup of size 3? Does it have a subgroup of size 5? Now, Lagrange's theorem is silent on that point. Yeah. It doesn't say yes, it does have one of size 3. Yes, it does have one of size 5. It says if there is a subgroup H, its size must be one of these. So Lagrange's theorem does not assert the existence of any subgroups. It merely just places a restriction on their size. Yeah. Of course, just coming out of the coursework. So a natural question, if D does divide the size of G, does G have a subgroup of size? Okay, so let's ask, is there a subgroup of that size? So if true for all G, true for all D, D dividing G, then we call G Lagrangian. It's got kind of a full range of subgroups of all the sizes they could have. Yeah. And in the coursework, you were proving that Dn is Lagrangian, that each of the groups are Lagrangian. Yeah. From the earlier work in chapter 13 it was, you learned that if G is abelian, then G is Lagrangian. So every abelian group has a full range of subgroups, or subgroups which exhibit all these possible sizes. But we're still, these are very special cases. So the dihedral groups are a specific family of groups. And abelian groups, they're very special groups as well. Your average typical group is neither Lagrangian nor abelian. And we have seen some negative examples. So this general question still remains. So the answer is yes all the time for these groups. Groups like this, but in general, the question still stands, and it does sometimes have negative answers. Okay, as you saw earlier in an earlier chapter. So from a negative example, A4, the alternating group on 4 letters, and well, the size of A4 was half of 12. Yeah, indeed. Well, you're right ahead of me. And what you should say. A4, what was it?
That does not have a subgroup of size 6.
Yeah. No subgroup of size 6. No subgroup of size 6. So there's 6 as a divisor of 12. We may have hoped, or we might have, it was maybe possible it had a subgroup of size 6. It wouldn't have broken Lagrange's theorem. But on close examination, it turned out to not have a subgroup of size 6. So sometimes the answer is yes, there are subgroups of these sizes. Sometimes the answer, or at least in one case there, the answer is no. So what are the Sylow theorems? The Sylow theorems, there's 3 of them.
It's weird to hear it said correctly, because I've always called it Sylow.
I
Sylow.
thought it was Sylow.
Well,
I've been reading Sylow this whole time.
Sylow, except I think the person Sylow was from Eastern Europe. I should know, Jan. Criticize me for not knowing.
It's all right, because I was calling
Somewhere.
it Lagrange when I first read it.
So Sylow, so it's W is in kind of F sound. Sylow theorems. So the Sylow theorems give positive answers to these questions. For certain divisors. Certain divisors of the size of G. So based purely off of the size of the group, there are certain divisors that we can say, yes, there are subgroups of that size in the group, even without knowing anything else about the group. Just knowing the number of elements that it has. It's worth looking at the statements of these groups, statements of these theorems, which we'll do now, just to look ahead and to see what's coming. And then we'll introduce the main tool, or review the main tool, which is the class equation. But is there anything just in that kind of page there that needs clarifying? Okay? Yeah.
It's from Oslo.
Oslo, Norway, indeed. So not Eastern Europe. East of here, but
East of here,
East of here.
East, comma, in Europe.
Right. So let's just glance at the statements of the theorems, just to, I hope you've done that already, but. So the first Sylow theorem says, if G is a finite group and P a prime, such that some power of P divides the size of G, then it has a subgroup of that size. Okay. So remember, the size of the group G factorizes into primes. Every integer factorizes into primes. If the power of a prime divides the size of G, then G contains a subgroup of that size. Okay. And this doesn't have to be the maximal power. You know, in the size, when you factorize the size of G, there'll be some maximum power of P that divides into it. This P to the R doesn't have to be that full power. It could be any intermediate power of P. The second Sylow theorem refers to these objects called Sylow P subgroups. Sylow P subgroups are, there's a little bit of a subtle point around the definition of them, but they're maximal P subgroups. Now you had this terminology a bit in chapter 13. Remember, a P subgroup is a subgroup where all the elements have order some power of P. Yeah. So P group is a group where you look at the orders of the elements and you only see elements whose order is some power of P. Different elements will have different orders, but all the orders will be powers of P. Sylow P subgroups are maximal such subgroups that are not contained in any larger P subgroup. So they kind of expanded out to their full size. You've got a subgroup which is a P subgroup, and you've grown it, expanded it out, and it's reached a maximal size within the group G. It's not contained in any larger containing P subgroup. Okay, the second Sylow theorem tells us a little bit more about the collection of such. So a group G can have many Sylow P subgroups for the same prime P. But what the second theorem says is that they're all conjugate to one another. So P1 and P2 are two such maximal P subgroups. We know that when you conjugate one, you can find an element, little g from the group. You conjugate one of them by G, you get the other one. So there's this kind of strong relationship between all the Sylow P subgroups. The third theorem gives us even more information about it. And the first theorem asserts that these subgroups exist. The second theorem asserts that, well, it talks about the maximal such P subgroups and says they're all conjugate to one another. The third theorem says something about the count of the number of them. And it says two things. It says the number of Sylow P subgroups, so two things about it. The count of the number of distinct Sylow P subgroups divides the size of G. So again, you've got divisibility going. Divides the size of G, and in addition, the count of the number of distinct Sylow P subgroups, it's congruent to 1 modulo the prime. That's quite mysterious at the moment. Why should it be congruent to 1 modulo the prime? Why should it divide the size of G? So these are things we're going to investigate and prove. It's giving you even more information. Okay? And all of this is based purely off of just this one kind of input into the whole thing, which is just the size of G. An integer factorizes into primes. That's where we pick up the various P's that we might apply this to. Okay. So these are our three theorems. And they are great tools to have to study the possibilities for groups of certain sizes, because they allow you to know and talk about subgroups of the group based purely off of the size of the group. So you're getting an awful lot of consequences about G just based purely on the size of G. Okay, that's the kind of surprise, or that's the impressiveness of these results. Okay, it's, just squeezing all these consequences out of just this one idea of the size of the group. Okay. So we're gonna understand these results and argue for them, and they all involve group actions. Okay. Now that's why you've been studying the last chapter. Do I need to say much about? Yes, those again to recall them to your mind. So group G, set X, which at the moment is just a bunch of elements. So G can act on a set X. So an element G, little g, becomes a bijection. Little g from the set X to itself. Okay, so you pluck an element G out of the group, and this becomes a function, a bijection on the set X. It sends X to itself. Notationally, we write gx. So I think at some points the book might have used the wedge notation as well, the upside down B, G wedge X. But a kind of simpler notation is, now, this is potentially quite confusing because you glance at that and it looks like a group product within the group G. Well, it's not. It's the group element G somehow acting on the element little x. Think of it like a function, f of x, g of x. Right? But the value it takes, this g of x is, of course, an element of the set, capital X. Now, it's not just any old, so there's some way of associating to every group element a bijection of the set X, but it has to have certain properties. And E, the element E, the identity, gives rise to the identity function. The identity function on X. Namely, EX equals X for all X and X. It's the identity function. It doesn't change things. So these are the conditions for qualifying as a group action. And secondly, the operation of the group product melds well with the creation of these bijections. Namely, if you look at the bijection that is generated by the product of two elements, it agrees exactly with composing the two bijections, G1 after G2 on X. Now, again, when you look at that, that seems very reminiscent of an associative condition within a group. That a product bracketed like this is equal to a product bracketed like that, but it's not that. It's different because the notation is meaning something different. This is a group element applied to the element X. This is like a function being applied to an argument. Yeah, and it's saying the function associated to the product of these two. This product happens inside the group G. The function that you get is in exact agreement with the composition of the individual functions you get from the group elements G2 and G1. So G2 is applied to the argument X, gives you some value within the set X, and then G1 is applied to that intermediate value argument to get the final value. And it always agrees with this. Now, when I think about these group actions, I tend to think of it in as something dynamic going on. I kind of think that the group is moving around the elements. So if you pick any element here, it corresponds to a permutation of the elements. So this little g causes each of these elements to zip around, and each one, and they move, permutes them all around. Or if you pick out, zero in on a single element here, yeah, and think of applying all the group elements here in turn to it, what you see is that each time you take a group element, it takes this point and it zips it across to another point. Or maybe sometimes these group elements might fix this point, some special behavior going on. Pick certain of these elements, it might move it around. Then you pick another element that it zips it up here. Interrupt at any time with questions. So orbits and stabilizers. You've got your group G, you've got your set X. The identity element is here. So if we look at a particular element of Y over here, there's a few things we can associate to Y. First of all, there's a special subgroup here, which is called the stabilizer of Y. Stab Y, or I think the notation uses is G subscript Y. It's the stabilizer of Y. So it's a selection of special group elements that have a special property that they fix Y. They stabilize Y. They don't move it around. This must at least contain the identity, remember? Because the identity, the bijection that's associated to the identity is just the identity function of the set. So at least the identity E always qualifies as EY equals Y. So the identity always qualifies as being an element of the stabilizer. There may be other elements. And it's actually a subgroup. So that's over here. Over here, we've also got orbits. So this is this curly O, script capital O, orbit of Y. So this is where you think of these dynamical metaphor. And this is the set. It almost looks, tells you why I have to think very clearly about things. Everything's related but different. So the definition of the orbit is you basically take these elements here and reverse their positions in the set closure notation. It's the set of every object gy as G ranges over all the elements of the group. So you just picked up those things and put them in the other positions in the set builder notation. This thing is a set of group elements satisfying a certain condition. This thing is a set of elements of the set X, one of them for every choice of little g from G. But it's always the same Y. So this Y here is a particular element. It always includes Y itself, because when you choose G as the identity element, E of Y is equal to 1. So Y is always an element of its own orbit. But it's a subset of the element. There may be other elements here. And Jan drew pictures where he connected all these by arrows. Yeah. Arrows here. Right? So these arrows are all the actions of the elements of G on Y. So hit G with one group element, hit Y with one group element, it comes out here. Hit Y with another group element, it comes up here. Hit Y with some group elements, it might just circle back to itself. So it's this bunch of elements that Y can orbit around. It's like a satellite orbits around the Earth. This is its range of positions under the movement of it induced by the group action. There was also a fixed set, which was kind of like this stabilizer. This was fixed set of G. Which was also got mentioned sometimes. And again, this is a set of all x's from X, such that G of X just X. So it's the set of all elements that are fixed by the bijection corresponding to the group element. So it's like a quick review of the definitions of group actions. One of the important theorems he proved was there's a very strong explicit connection between stabilizers and orbits and between their sizes. The size of an orbit of X, orbit of Y, I'll write it here. The size of the orbit of Y is exactly the index of the stabilizer of Y and G. And if we're talking about finite groups, so the index remembers the number of cosets of the subgroup within the large group. But for finite sets, it corresponds exactly to quotient, the size of G divided by the size of the stabilizer. So the bigger the orbit, the smaller the stabilizer, and vice versa. Okay? So they have a reciprocal relationship in their size, governed by the size of G. Now, all that's generic. We could be speaking of any action. We didn't nail down what the action was. We just gave it a set of conditions. Something had to be satisfied in order to be called an action. Now we talk about a specific action, and it's G acting on itself. So these two pictures are kind of merging into one, although sometimes it's still helpful to think of them separately. But now the set that we're acting on is actually the group itself. So it's G acting on itself. And this is going to reveal a lot about the structure of the group and the types of subgroups. G acting on itself by conjugation. I mean, there might be many ways in which the group can act on itself. But it's the self-action by conjugation. So you take an element, little g, the mapping you get, the bijection, is to send an element h to GHG. Yeah? That's the conjugation of h by g. So h maps to conjugation of h by g. Now, some of the terminology is specialized here as well. You remember? The orbit of an element h, which is by definition the set of all conjugates of h. G, little g roams over all the group elements of the group G. This is called the conjugacy class. Conjugacy class of H. It's the orbit. Okay, look, when you're talking about this action, there's a special term, conjugacy class of H. The stabilizers also have special names. So the stabilizer of H, which is the set of G, such that G, H, G inverse is equal to H. Or another way in which this is also written GH equals HG. It's another way of writing that condition. multiplying both sides on the right by G. This is called the centralizer of H. It's often written as C of H. Now, the class equation. The class equation is the main tool, or one of the main tools in this chapter. It's kind of the class equation. So it's the central, or it's the beginning thing we focus on, that we build our proofs on. And in some sense, it's a nice intuitive idea. It's an equation for the size of G. It's a nice way to count the elements of G. And we count them. Remember, in any group action, the orbits always partition the set that you're acting on. Okay? That was another thing you discussed in that chapter. There's a particularly kind of special bunch of orbits which are singleton orbits. Each of these have one and only one element in them. A typical orbit you expect to have multiple elements in it. Yeah? Typically. Frog spawn or something. So typically your orbit has many elements. Now remember, it's not like the partition by cosets. The partition by cosets was quite special. Every subset had exactly the same number of elements. And you partition the group by subsets of the subgroup to prove the Lagrange's theorem. Here typically you see a range of different sizes. But it's a partition. You have the set G split up, right? Some of them are kind of special in their singleton sets, one element sets. So the class equation is quite simply counting the elements of G according to the partition by conjugacy classes, which are orbits of the action of G on itself by conjugation. So, if you've got this picture floating around, it immediately gives you a sensible way to count the elements in G. The total number of elements in G are the number here, plus the number here, plus the number here, plus the number here, plus the number here. You just add up the population of each set. Yeah? It's a sensible way. Population of Britain is England plus Wales plus Scotland plus Northern Ireland. No, population of America. Yeah, so whatever partition you've got, you can count them all. So I'm probably not even going to get to the first thing. I'll prepare for tomorrow. But how do we note this down? So what we've got is what we notate a set of representatives. So we pick an element out of each one. So x1, x2, x3, x4, and so on. So you've got, and I'm going to represent remember the size of the orbit is the index of the stabilizer. So in this language, the size of the conjugacy class is the index of the centralizer. So the index of the centralizer of x1 in G, this is the size of the orbit containing x1. You add to it the size of the orbit containing x2, and so on. Now it's a finite group, so there can only be finite many of these things. up to xk. So this is the last one here, xk. Okay. There's one more term we're going to add to this. One more term we're going to add to this. The xi here, the xi are representatives for the non-trivial conjugacy classes. Non-trivial meaning size or order strictly greater than one. Only that have more than one element. Like this one, this one, this one, this one. As distinct from these special singleton ones that we group together. The singleton ones we group together and count them in one go with one term in the class equation. And it's ZG. Remember Z standing for Zentrum, German word for center. Center of G. Remember, by definition, the center of G is the set of elements. Yeah, let's write it like this. The set of all X, an element of G, which that's for all G, G, Gx equals Xg. Center was the special elements that commute with everything. It always contains at least the identity. The identity commutes with everything, so the identity doesn't change it. A typical group might have a non-trivial center. Some collection of special elements that have this very special elements X that have this special property that they commute with everything. But when you compare this definition of the center with the definition of a conjugacy class, see, look, what happens when you do Gx, G inverse? You get just equal to X, when X is an element of the center. So actually the center, another way to think of the center, it's the collection, it's the grouping together, the union of all these trivial singleton conjugacy classes. The union of all the single element. Singleton is an element, a set containing one element. All the single element conjugacy classes. This group of little box-spawny things. If you want to, maybe you would continue the class equation by having, you could continue it in the same way. These terms refer to the count of the number of elements in these conjugacy classes. Maybe you'd have, plus one, plus one, plus one, plus one, plus one, plus one for each of these singleton conjugacy classes. But it's maybe a good idea to, since the lot of them together actually form a subgroup, a special subgroup of the group, the center, it kind of makes sense to group them all together there. So this is the class equation. So it's quite a intuitively simple idea. You're just counting the number of the things in G according to this partition. Okay? These are the size. So this is the way it's normally presented. But alternatively, you could think of it as the size of the orbit of x1 plus the size of the orbit of x2, etc. Plus the size of the orbit of xk. Here they're just represented as the index of the centralizers in there. And then plus, well, you could have one extra term for each of these single element things, but they gather together to form the center. Yeah, so you're saying, to calculate, if you were to calculate these, you need to know the size of G in order to take
And
the
that's what
equation.
I was like.
And it's giving you an expression for
Yeah.
G. Yeah.
Yeah.
But typically, we tend to think of this thing, we tend to know the size of G from the very beginning.
Yeah.
Because often we pose ourselves the problems, how many subgroups are there of size of 100? So very much we're kind of arguing, you know, how many different groups are there size of them? This class equation will be an important tool to answer. So it's not a formula that's going to help us find out how big the group is.
No.
Rather than that, it's an interesting expression of the size of the group. It's an interesting breakdown of the size of the group, from which we're going to learn stuff, from which we'll be able to draw deductions. Yeah. Rather than as a solution to the problem of, oh, how do we find the size of the group? Yeah. Do you get it?
Yeah, I do. It's just like that thing though, you know, when you use a word to define it itself.
Yeah,
You shouldn't do that,
yeah,
and I feel like we're doing that.
Yeah. If this was the answer to the mystery of how do we calculate the size of G,
Yeah.
it would look self-referential. But it's not. It's more an interesting view on the size of G, which does refer to itself, of course. Yeah. In that view, in this view less so.
Yeah, that better one, that one.
Yeah. So I've probably not given myself enough time to embark on the proof of Cauchy's theorem. But let's at least look at the statement of it.
6 minutes.
That sounds mid.
Go.
Or first of all, just pause for questions. So that's why it's worth spending this time on establishing the class equation, because we're gonna run from that now. So I definitely encourage you in advance of tomorrow's lecture, definitely read through all this again and try and get acquainted with it, because I want you all to feel good about this equation and to feel confident about it, because the arguments are all going to build from that. So theorem 15.1 is our beginning, and it's our first positive assertion statement about the existence of certain subgroups. And this says simply, if P divides the size of G, then G has a subgroup of size P.
Yeah, I do what it's got random music.
P is a prime, so this subgroup is cyclic. It's isomorphic to ZP. It's generated by an element of the group of order P. All equivalent ways of saying it. Book uses induction. Yeah, we can kind of launch into the induction case of this.
Tuesday written all over it.
Yeah. My thoughts exactly. But one of the good things about the class equation is you can see at the moment we talked a lot about divisibility. Does this prime divide the size of G? Does this prime to this power divide the size of G? Lagrange's theorem says if there's a subgroup that has to divide the size of G. But what's new here, what's going on is suddenly we've got an additive thing as well. And rather than just talking simply about multiplication, everything dividing everything else all the time, now suddenly we've got an additive formula. And I think the combination of those two, not only is it additive, but also some of the terms are quotients of the size of G and the size of the subgroup. So you got a good, nice mixture of additive stuff and multiplicative stuff.
They're not all subgroups, are they?
Well, no, these things are sets, but their size is given by a quotient of orders of groups.
Yeah.
The index, the size of G divided by the size of the centralizer. The centralizer is a subgroup. Yeah, so that's important.
They still have to divide the order of G. Like the order of the sets has to divide
Yes.
the order of G, but
Yes.
they're not subgroups.
They're not subgroups. Yeah, no, these are very much not subgroups because the identity is only located in one of them.
Yeah.
In fact, where is the identity here?
So,
On its own, indeed. One of those singleton, one of the frog spawn things. One of these is the identity.
So we're gonna write probably.
That's on its own.
You were so proud of that, but we knew it was in, but we know it has to be in the centralizer. Like,
even if you didn't know it was on it, so
It has to be, yeah, that's good. Has to be the centralizer, so it has to be one of these ones that's making up the centralizer.
I'm sorry, you were just really proud of it.
I'm proud that I've understood something that I missed all
Well,
the lectures for.
she's actually proud about making a joke about them being lonely on Valentine's
And
Day.
that I'm also proud of that.
Because they're single. Because they're singles. If only it wasn't past that day. It was only 4 days ago. People still.
Okay, so tomorrow, I'm not gonna review all this again. We're just gonna
Yeah,
start
yeah.
from here.
The dad.
I'm gonna be walking the door talking to you, okay?
Okay.
I'll have started my laptop recording as I walk in the door.
It's fine as long as you show up late.
Okay? Okay, we'll see you then.